Yeah. So I will start with like the really like textbook machine learning slides, which are basically the formulation of the learning problem. And what we typically have in machine learning is some data which we would like to predict or classify. And for the sake of simplicity, let's assume it's a vector in d dimensions. And then we have something, it still doesn't work. Yeah, no, it works. It's the target. And the target is what the machine learning model should do, predict. And it can be, for example, predict some price, predicting some property of a system, and so on. Again, for simplicity, we can make it real valued. So it's, of course, all these things can be made much more general, but it's just to basically give the main ideas here. And one of the main ideas is to say that basically our data is coming from some underlying probability distribution, which basically is the way data produces in reality. What we can expect, basically, our model would see at test time when it is deployed and when it has to actually perform decision-making or predictions. Then you have predictions. So this is basically the f is your model, and f of x is basically the function. F of x is the output of this model, which will try to be as close as possible to the targets. And you can measure that by some loss function. And the loss function, you can think of it in terms of cost. So how much it costs to make a certain prediction, given that you had to reach a certain target. And if you want to think of the word loss, it's really how much you would lose from doing that. So here is a small diagram which puts everything together. So you have basically a probability distribution P, which is basically generating data, which are basically the input and the output of your model. Then your data, your input X is processed through some function F. It produces some output Y, and then you have this loss function, which tries to tie the prediction and the target together. So then the loss function just tells you something about the cost for a given data point. But of course, what you want to optimize the cost on average, what you will lose altogether if you apply your model on some distribution. And this can just be done through integration. So you have your loss function, which you integrate over your whole data distribution. And there are things that are fixed. The probability distribution is fixed. The loss function is fixed. What you can choose is the function f, right? Function f is what your machine learning model, what you want to learn. And so essentially, you will do argmin over f, and you get basically your optimization problem. So most of the time, this is exactly what you want to do if you have properly defined your distribution P, if you have properly defined your loss function L, then this will basically produce a classifier or a machine learning model which minimizes the cost or maximizes the reward. Okay, so this is the formula I was just showing in the previous slide. And now there is a caveat with that. The caveat is that the distribution P of X and T is never really observable, never really accessible. We don't know exactly what will happen at test time. So it's not just a memory exercise. We only have access to a data set. So basically this P, which is here written in red, has to be replaced by something which we have. And we have this data set. And so essentially, you can think, I'll just put some diagram here with x1 and x2, so two measurements. And maybe the true distribution would be some kind of blob here, continuous blob there for x1 and x2. Basically the red and the blue markers here. But you don't have access to this continuous distribution. You just have access to a finite sample. And this is basically your data set. So your data set, it's a pair of input and target, a collection of pairs of input of targets, and it is indexed by 1 until n. Here, I just make a small remark about the notation, which might sometimes appear inconsistent. You see that what you have here in the D is x1. X1 is in bold. it means that basically you are indexing, the index corresponds to the data point. While on the right-hand side, you have the dimensions, x1 and x2, and that means specific elements of the distribution of the vector of the vector x. No? So you have sometimes these two conflicting notation. As much as possible, I try to resolve that by putting the x in bold when the index is a data point, and in non-bold when the index is a dimension. No? Okay, so we have to address this degraded scenario where you have limited data. No? And the most straightforward way to address it is to say, well, I don't have P, but I have an empirical distribution which consists of my data set. So you can basically think of your distribution P as a bunch of Dirac function which you place exactly at your data point to divide everything by 1 over n. You divide everything by n. And this gives you a modified objective, which is the minimization of the empirical loss. Okay, so sum over all the data points and the cost of classifying the specific data point x, given that the target is t. So this looks straightforward, but there is a caveat with that as well. So this is basically how you can think of it in a graphical way. So you have, as your input, you have the data input space. On the vertical axis, you have the targets. And in blue markers, you have the data sets. And you have only a few data points. You have your function that you learn. This is this curve, which you see in black. And for every data point, you have a loss, which is basically the cost of not reaching exactly the targets. Here they are denoted for every data point as vertical bars, and the idea is to try to make these vertical bars as small as possible. But there is a problem with that, is that depending on, if you don't specify any constraint on your model, the model might just be fine adjusting its values near the available data. And then you cannot say anything about what the model will do on a data point that it has never seen in the data. And this is the problem of overfitting. No? So it fits the data, but fails to produce something which really nicely generalizes. So there are variety of ways to deal with overfitting, and here I will present one which is very basic, which is to try to make a distinction between functions that are immune to overfitting and some functions that are basically the function that do not. So functions that are immune to overfitting might be, for example, functions that have a few variations. It's very difficult to fit every data point using, for example, a constant function. And also you are kind of sure that it will generalize better. So you will define this set of function calligraphic f, which you see here in green. This could be something like that. So every function which is low varying, you accept it, you take it as part of this set, and functions that are highly varying, you discard them. So here you don't care so much about matching the target, you just try to define what is a function which is okay to be part of the optimization and which one is not. And so here we'll basically restrict our search over the space of functions which are low varying. Okay, and then you can basically just take the same equation as you had in the previous slide, but you are adding this additional but crucial constraint, which is that you have to minimize in the set of smooth or overfitting proof functions. Okay, so now big question. And now we are basically moving away from the problem of optimization to the question of specifying f. Because these things, usually we can optimize them pretty easily. There are tools like gradient descent, stochastic gradient descent, but it will turn out to be much more crucial to specify the proper set of functions, f, because if we have the best optimizer in the world and it produces, it produces this function, This is no good. Okay, so we will make two scenarios, and the first scenario is when our data is a simple IID according to the underlying distribution. So we really assume that what we have in our data set is what will happen really at test time, but we just have a few samples, a small sample. And one approach to deal with that in the context of separating data, classifying data, is to restrict the function to be slow varying. So you can, for example, think of your function f of x as being like your prediction. If you predict above a value of, let's say, +1, you predict in the blue class. If you predict, if the output is below -1, you predict in the red class. And if you are between -1 and 1, you are in some gray zone where you can't do, where you can't classify, right? Where you will basically have the cost of failing to classify. And so now you have this vector W, and you will try to control how large it is, so basically how flat your function is. The flatter it is, the less you will be able to classify. If the vector W is 0, then all your outputs will be 0, and basically everything is in the gray zone, nothing gets classified, you have a huge cost. But you still don't want W to be too large, because then you have too many variations, and you are not able to generalize to new data points. You'll basically start overfitting your training distribution. So what you want the norm of W to be smaller or equal to something, and typically you write it as 1/n, where m can be understood as the margin from the middle of the gray zone to the location where things start to be properly classified as blue or red. So the idea is that we set a margin. We say, okay, this is a reasonable margin for my given problem, and you minimize within that class. And what you can see is that if you apply this technique, and this is basically the basic idea behind support vector machines, or more generally, large margin classifiers, it significantly reduces the gap between training and true error. And there is even some theory about that, and you might have heard of some kind of the foundations of machine learning, the VC theory by Vapnik. And but this basically applies to the scenario where the data is assumed to come IID from the distribution P of x and t. And in fact, this is not always given, and in the majority of cases, we will not have that. The more frequent scenario is when the data comes from a different distribution, Q of x different from P of x, and it might be, for example, because for some classes you have taken different data sources. So you might have a lack of representativity. For example, if you try to classify between A and B, maybe for the group A, you don't have like sample across all ages, and for B, you have a different group of ages. And you have start to have this kind of spurious correlations, which we'll see are becoming very problematic. And especially if you apply the idea of a large margin, which I was discussing in the slide before, you will get something which is like that, which basically will separate space both on x1 and x2 in that case, even though, remember from the previous slide that the truly discriminative feature was x1. So applying a large margin, applying the standard machinery of regularization will not go very far. So in practice, it's also very difficult to try to fix this machinery to handle that case, because it might seem very arbitrary. If you just have access to this data, it's very hard to say, well, in fact, the relevant feature is x1. You might use things like sparsity, you might use like other techniques, but ultimately, it is not guaranteed that it will find the right decision function. So ideally, we would like to be able to specify this function f to ask basically the human, okay, which feature is actually relevant, which one should I look at for building my classifier. But it turns out that actually things are even more complicated than that, because if you think, for example, that your input is images, where basically every feature is 1 pixel, then you might not be able to identify exactly what features are relevant, which one are not for predicting. Because sometimes the features, the correct feature and the wrong feature, they are entangled within the same pixel, or they occur at many different locations. So here what we would say, well, in fact, to predict this class cartoon from the data, you would need to basically remove almost all the old input features, but you will lose a lot of information as well. So basically, this is hard to choose the function f at all. And this makes the transition to the second part of this talk, which will be to try to just learn the machine learning model without taking too much care about setting a proper class of function f, and then look what the model has learned, because maybe it has naturally used the right features, and then we're basically worried about nothing, or it is using a wrong feature, and then we can just go back to the drawing board, trying a new model, and then repeat the process. No? So this is basically the idea of explainable AI. And here I will be very shallow on explainable AI, but just to give basically the main idea, which is that you have some input. It can be an image consisting of several features. Then you pass them into your machine learning model, typically a deep neural network. And you have something at the output, which can be typically interpreted, for example, as evidence for the class motorbike. Then what you would like to do, you would like to decompose the output score into contributions of different input variables. And you can denote this contribution as R1, R2 until Rd, where D is the number of dimensions. And what you typically require is that these contributions are additive, which means that you can think of them as the share a given feature contributes to the output score. No? It's a property which is implemented in many explanation techniques. And this turns out it's not a easy problem. In fact, it is one of the main themes of explainable AI. Try to solve this problem in a systematic and a theoretically well formulated way. And there are some approaches like Shapley values, backpropagation, LRP, and so on that are trying, that are taking the different approaches to solve this problem with different results in terms of explanation quality. Here I will just present briefly layer-wise relevance propagation, which basically address this problem by thinking of your classifier as a sequence of layers, a sequence of processing layers. So it can be a neural network, but it can also be something more classical, like a Fisher vector model, which consists of a few hard-coded stages. And then you start from there, and you will see at the output of your classifier some score, evidence for example, here the class bike, and you propagate it based on specific propagation rules, which basically identify what are the structures, internal structure of the classifier, which have contributed to the prediction. And you, because you have like a composition of this function, you are doing this iteratively until you reach the input, and you have this property, this rule are designed in a way to enforce the conservation of relevance, which means that at the end, you have an explanation where if you sum the value over all features, over all pixels, you have basically the value at the output of your model. So it's a way to identify what contributes to the prediction of your model. And here you see at the end of this procedure, you have a heat map, which tell you what the model has looked like, has looked at. Here you have a bike, and it has identified, for example, the wheels as being responsible for the class bike. Okay. Now, sometimes you have also funny thing happening, right? if you think of these images of a boat, they are classified as boat, and you're wondering why are they classified as a boat? You would expect they look at the boat. No, but they look at the water, which just happen to be very often there when there is a boat for good reasons. Also some more funny things here happening. You have basically some image of a horse classified correctly into as a horse, but if you look carefully at what the model uses for predicting this image, it doesn't look at the horse, it looks at this copyright tag, which you have at the bottom left corner of the image. And if you remove this copyright tag, then the model is completely lost, and it has really a hard time predicting this thing to be a horse. So this is basically something which we call the clever hands effect. It's when a model predicts correctly on the given data, because the data has this correlation, for example, boat, water, or horse copyright tag, but is not expected to work well on the new data, because as soon as you put a boat standing on the grass, for example, which happens sometimes, then it will stop working. And same for these images of a horse. As soon as you remove the copyright tag, or you add it on some other classes, you will start to have some prediction errors. So this is a little bit like the same drawing as I was making in the previous slide, where you have your two features, x1 and x2. x1 is the boat in that case, x2 is the water. x1 is the feature you should use to produce a good model, but the model just look at the data and think, oh, let's try to use both. And in fact, the water is just so easy to detect that I will use mostly the water. Okay, so this approach, basically, which I was showing before, allow you to accept a classifier as doing the right thing, or reject it and going back to the drawing board. But in practice, what you observe often, and this is, for example, the dataset ImageNet, a bit more complex dataset with 1,000 classes. And you have here images of the class cartoon, which are predicted correctly by the model to be of the class cartoon. And you see that it uses some features which are correct, but also some features which are incorrect. And you have this watermark, which come at the center of the image, which is picked up as evidence for the class cartoon. It just happened the data was collected in a way that many of these images had this watermark, and the model found that out. So you have basically these multiple concepts which are entangled in the same explanation. And then ideally what we would like to be able to keep the best part of the model and rework the one that fails. For example, remove its contribution from the overall prediction to arrive at a more robust model. And this was some work of us with my colleagues, which was recently published. And it looks at the problem of trying to extract subspaces of explanation. Try to break down this explanation into sub-explanations that identify the different components of it, the different sub-strategy the model uses for predicting. And so it's very difficult to disentangle things in the input space. So what we said is, okay, let's look at the latent space, vector activations. And then we will introduce what we call a virtual layer, which does some projection and back projection. So if you insert this virtual layer in your network, it doesn't change anything. You have effectively the same function. But now you can design some of these subspaces, trying to have them capture different aspects of the decision strategy. And once you have extracted this subspace, then you can basically run this relevance propagation ID and filter it through the different paths. And as a result, you get different explanations, a different subset of the explanation. Also, a nice property of that is that if you sum up all these explanations, then you get the original standard LRP explanation. So the question is, how can we actually learn these subspaces? Because if we set them at random, it will not work. And we'll basically apply a we propose a new algorithm called disentangled relevant subspace analysis, which works as follows. I will introduce a bit of notation. So this is basically I, N, and K will be how we index the neurons, the data points, and the concepts. Then we have some activation vector, which is basically what you had in the previous slide, where we want to basically build our subspace. And then we have a response vector. So you see different name for it in the papers. Sometimes we call it a context vector. But we can think of it as if the model were linear, this will be the weight of the model. So it's basically telling you how the model will respond to specific activations. So it's of the same dimensions as the activation vector C. And then you have this matrices UK, which are basically blocks of your orthogonal matrix U, which define the different subspaces. So now, the first thing you can do, and this is not this work specifically, it's basically the general structure of explanations, of classical explanation, is that basically if you want to ask whether a neuron is relevant or not, it has to be both activated and the model has to respond to it. If the neuron is off, but the model responds to it, then it does not contribute, it is not relevant. If the model is if the neuron is activated, but the model is invariant or does not respond to it, again, it does not contribute. The only way for this neuron to contribute is if it is activated and the model responds to it. Okay. Now what we would like to find basically not neurons that are relevant, but subspaces that are relevant. And so basically if we perform LRP, but don't stop at the level of neurons, but stop in the middle of the subspace, so in this virtual layer, we can actually get a closed form expression for the relevance of subspace K, which is basically the projection of the activation times the projection of this response vector. And the subspace can be one-dimensional, but it can also be multi-dimensional. So typically we might have like 100 dimensions, which we want to partition into 4 subspaces of 25 dimensions each. And so you have basically this small dot product in the middle, which effectively is a pooling of the relevance over all the dimensions of the subspace. And what we will also add is a rectifying term just to focus on the positive relevance. So through that, we'll ignore what happens to negative relevance. It's more like a technical detail, but it's still crucial to make that thing work. And now comes the DRSA objective. What we will try to do. So RK is the concept, is the relevance of concept K for a given data point. What you have here, RKN, is the relevance of concept K for the data point N. So now, think of your concept K. You want your concept K to activate or to be relevant only rarely, infrequently, but when it is relevant very strongly. Because you might think, for example, that this copyright tag, which you see in some of the cartoon images, they appear either not there or they are there. So it's not something which is just like continuous. So we'll apply basically some kind of max pooling to extract basically to kind of capture the tail of the distribution of relevances along concept for concept K. This is the purpose of the S-max. Very similar idea as, for example, kurtosis-based independent component analysis. We are trying to learn the tail, not of the distribution in that case, but of the distribution of relevances. Try to find some kind of independent components. And then we have another operator in our objective, which is the soft mean. And the soft mean basically requires that there is no component which models nothing. So basically what you don't want one of the components to be just left doing nothing, because otherwise it will drag your minimum to 0. and you will not be able to maximize your objective. So you have this nesting of max and min. The first one serves to produce this, try to align the subspace with the tails of the relevance distribution. And the second one will try to balance the load between the different subspaces. And in practice, this S min and S max, we choose them to be some generalized means, one which is essentially the L2 norm, and the other one being the L0.5 norm, if I can talk like that. Okay, and so this is fundamentally, or in a very specific way, different from representation learning, because we don't focus on what is expressed in the data, but what is relevant in the data. So just to give a bit more detail on that, if you would replace C by A in this equation, then you would fall back to something very similar to ICA, independent component analysis. So what is crucial here is that our analysis looked not only at the data, but at the response of the model. So that if the model does not look at all at some of the features, then the formulation of objective will not waste time trying to model that part. It will really only focus on the few features which the model actually uses for its predictions and try to disentangle that. So just a quick recap. So now we have basically an algorithm to optimize these subspaces UK. And we have a propagation or an explanation technique which can basically propagate through your network and be filtered based on these subspaces. And out of one image and one explanation, we can produce multiple components of that explanation, which ideally would produce correspond to distinct aspects of the strategy. This is, again, our carton example, where we were unsatisfied because the explanation was entangling different aspects of the strategy. And this is what our DRSA optimization, which basically disentangled this explanation in multiple subspaces, called here S1, S2, S3, and S4, produces. And so you can see, for example, that subspace 1 is looking mostly at the geometry of the carton, right? So it seems to be legit. Subspace 2 looks at textual markings on the carton. So here we have to start to be a bit careful. But if you think about that, it's still a valid strategy because a lot of cartoons come with textual markings. Why not use this information? Then you have S3. Here it looks a bit at the bottom of the cartoon and also captures some small logo at the bottom right. So here we are at a bit already suspicious. And subspace 4, we see this huge red watermark in the middle. And clearly, that's something you would like to discard in your classifier, because you cannot expect that at test time, depending on the application, at least, images of carton will come with this watermark. So ideally, you would like to remove that feature from the model and try to rely mostly on this more robust, really like more robust features which are focused on the actual object. And so now that we have disentangled these 4 subspaces, what we can do, and here we are using a property, which is that the conservation of the explanation allows you to think of the output as basically the contribution of the sum of contribution of each subspace. So each subspace basically contributes a certain amount, and you can see that's okay. Here for the last image, 11, the output of the model corresponds more or less to 11 plus 7 plus 2 minus 10. And so what we would like to say, okay, well, let's try to prune the subspaces that are identified to be of Cleverhand's nature. And here the user has to basically come in the loop and give feedback. Then, as you see, it's not perfect because you have also some blue copyright watermarks in the other subspaces. You need to adjust a little bit the threshold, but fundamentally you have still rectified the flow decision strategy. And this is what you can get. So basically you can get, in this case, on some simulated test time distribution consisting of poisoning the data 5%, these watermarks, an improvement of 3.6%, I think. No? So basically, without having to intervene into the data set, without having to have access to all the data in the world, you were able to improve the accuracy of your classifier. Okay, so this is basically the general idea, and now I will try to tie it back again to the problem of optimization. Let's just try to recap briefly what were the main steps this presentation. So you have basically machine learning, which comes with a well-defined cost function, which consists of minimizing the expected cost, loss function integrated over the distribution. This you can't do in practice because you don't have access to the distribution P. In practice, you can only rely on empirical data, and to translate this equation with the data you actually have, you have this sum over your data points. But many functions can fit this objective perfectly, right? Some might generalize better than others. And what is really critical here is to choose a possible set of functions f, which will produce the desired generalization. But again, it might work in the context of IID data, but if you have spurious correlations, then it will not work well. Okay. So what we have to do, or what we can do, we can use explainable AI to basically place the user in the loop, trying to say, okay, well, we have used this set of possible function f, like all the possible neural networks in the world. We've been optimizing through them, and as a result, produce or train neural network. Is it doing the right thing, yes or no? But more than that, we wanted our explanation to be actionable so that we can basically, in one step, correct the function to remove it, its incorrect part from it to arrive at a better classifier, which generalizes better. And this we have formulated as an optimization problem, DRSA. So and be like just an outlook also for the optimization people, is that you can try to solve an optimization task which consists of minimizing your cost function, but ultimately the bottleneck is not so much the optimization technique itself. I mean, of course it is in certain contexts. If you think about foundation models and so on, you need a lot of GPUs, but also a lot of smart tricks. But it's also about the specification of the function, especially when you have limited data. And what could be interesting is if you try to think of optimizing the way the user is involved in the process of specifying or correcting the function. And so one baby step here is DRSA, but I'm sure there's much more that can be done. So I'm done. Thank you for your attention.